let's take a look at some more complicated trigonometric equations that involve a little bit of algebra. So sometimes you might see some problems that look like the quadratic equation. So you might have to use the quadratic formula to solve those types of problems. Okay, so just keep that in mind. Sometimes you might have to factor. Sometimes you might have to do a little bit of math, some identities, which we'll do in a second. So just be very aware of that. So let's start off with this problem. So find all the solutions from 0 to 2 pi. So we got secant x sine x minus 2 sine x equals 0. So the first thing that I see is I see two terms, and they both have a sign. So let me go ahead and factor out a sign. So you're left with secant x in the middle, in the inside, and then a minus 2. Okay, so factoring out that sign actually did help a lot. And I can set both of these guys equal to 0. So sine x equals 0, and then secant x minus 2 equals 0, which gives me secant x equals 2. So this guy is better to be written as a cosine. So 1 over cosine of x equals 2. This is going to give me cosine of x equals 1/2. So we have two candidates. We got sine of x equals 0. And we also want to find all the solutions where cosine of x equals 1/2. So recalling the unit circle, we only want from 0 to 2 pi. Luckily, these values are all in the unit circle, so we can go ahead and take a look at that. So sine of x is going to be at 0 and also at pi. Okay, so x here is going to be 0 and pi. So those are the two solutions. And now cosine of x is going to be equal to 1/2 at pi over 3 up here. And it's also equal to 1/2 down here at 5 pi over 3. So x equals pi over 3 and 5 pi over 3. So all of these are going to be my solutions. 0, pi, pi over 3, and 5 pi over 3. Okay. Let's take a look at this guy. 2 cosine squared plus cosine x equals 1. So once I see a squared, it immediately makes me think I have to use the quadratic or I have to use some sort of factoring. So let me move the 1 over because I see some sort of quadratic equation. So it's better to set it equal to 0. And now let's go ahead and factor this guy. So this should be 2 cosine of x. This should be cosine of x. It seems that both of these guys should be 1. And because the cosine is positive, this should be a positive. This should be a negative. So you get that 2 cosine of x minus 1 equals 0. And then cosine of x is equal plus 1 equals to 0. So here you get cosine of x equals 1/2. Cosine of x equals negative 1. So we got to take a look at where exactly the cosine is 1/2 and where the cosine is equal to negative 1. So cosine is going to be equal to 1/2. Well, we already saw that, right? It's at pi over 3 and 5 pi over 3. And then the cosine equals negative 1 down here. No, wait a minute. It equals over here. Here's a cosine, so it's at pi. So you're going to have 3 solutions here. Okay. Again, if I was asking for all solutions, we would add plus 2 pi k. Okay. Now let's look at this one that looks a little more challenging. So I don't know if this is factorable, but let's go ahead and try to factor it. So I see a 2 cosine x here. Cosine x here. Put a 3 here and a 1 here. So do it. Oh yeah. Both of these guys are negative. Okay, cool. All right. One thing that you could have also done is use quadratic formula as well. Okay, you could have used quadratic. Okay, so we're going to do, and that should work. Negative 6, negative, yeah, perfect. So you got 2 cosine of x minus 1 equals 0, and cosine of x minus 3 equals 0. So here cosine of x again equals 1/2. So this is boring because it's the same thing, pi over 3 and 5 pi over 3. This guy is a little weird, right? Because you got cosine of x equals 3. 3 is not in the unit circle, but this should raise a little bit of alarms because this is exceeding 1. One other thing that you can do is you can always take cosine inverse of 3 to see what you get. And what you should get is no solution here. So this exceeds what we want. So these are the only two solutions. All right, and now let's take a look at this guy. So this looks like another quadratic. So I'm going to move the 2 tangent over. Get tangent squared x plus 2 tangent x equals -1. And let me add the 1 over, so you get tangent squared x plus 2 tangent x plus 1 equals 0. And I think this should factor. So you get tangent x, you get tangent x. It should be both a plus 1. So you basically got two of them, so you only got to do 1. Tangent of x plus 1 equals 0. So I can subtract by 1. Equals -1. So -1 is going to be here, and then also here. Okay, so then this will be 3 pi over 4, 4, 5, 6, 7 pi over 4. And we're only looking at from 0 to 2 pi, so x is going to be equal to 3 pi over 4, and also 7 pi over 4. Okay, cool. All right, and now let's go ahead and do the ones with identities. So here, literally, you just have to really just try your best to do these problems. You can try to solve them using trig equations. I'm sorry, using trig identities. So you would have to go back to the trig identities and see what this best looks like. So again, this one can be a little challenging, but I think it can be really easy to do. You just have to try some identities out. So the first thing that I see is I see a sine, a cosine, and a sine. And one of the things that I prefer to do is have everything as one trig function. So I'm going to leave the sine x and the sine x is by itself because those really aren't doing anything for me. So you got sine x, sine squared x, and the sine x. And then what I'm going to do is I'm going to have that cosine squared and change that to a sine. So I know this guy right here. Well, I know cosine squared x is also equal to 1 minus sine squared x, if I flip it around. So this guy, I'm going to plug in 1 minus sine squared x in there to make everything into a sine. So you're going to have sine squared x minus 1 plus sine squared x minus sine x equals 0. So I get sine squared x and a sine squared x. That gives me a 2 sine squared x minus sine x minus 1 equals 0. So another quadratic equation. So I'm going to get 2 sine x and then a sine x here. A 1 and a 1. This should be a minus and this should be a plus. So you're going to get 2 sine x plus 1 equals 0. And then sine x minus 1 equals 0. Remember, we want the solutions from 0 to 2 pi. So sine x equals -1/2. Sine x equals +1. So looking at our unit circle, if you look at sine x of -1/2, that should be negative down here. So that's at 7 pi over 6. And it should also be -1/2 over here, which is 11 pi over 6. So this is our first two solutions. And sine of x equals 1, well, that's going to be up here at pi over 2. So these are going to be my 3 solutions for that problem. All right, so now let's look at this guy. So sine 2x minus sine x equals 0. So this looks like a double angle formula, right? Sine 2x. So if you remember, sine 2x is just equal to 2 sine x cosine x. So that's this guy. Then I have the minus sine x equals 0. So reducing that makes it a lot easier to work with, because not only do we want to have just the same trig function, it'll also make sense if you also just have the same argument. So the thing inside of the trig function is better to just have it as a single x, not with a double or a half or anything like that. So here you can see you can factor out a sine. So you got 2 cosine x minus 1 equals 0. So we got sine x equals 0. And 2 cosine x minus 1 equals 0. So you get cosine of x equals 1/2. Alright, so let's look at the unit circle. So sine of x equals 0. Okay, so we're looking at all of the y values where they're equal to 0. So you can see that that's going to happen at 0 and at pi. And then cosine of x equals 1/2. We've done that, I think, a million times. Pi over 3, and also 5 pi over 3. Now, also do note that as I'm doing these problems, we're doing 0 to 2 pi, but I could have easily set 0 to 360 degrees. If I would have set that, that means everything would have been in degree mode, not so much in radian mode. Okay, and now let's finally do our last example. Okay, cosine 2 theta equals 9 cosine squared theta minus 4. Okay, so here we got to think about how we can reduce this cosine 2 theta into maybe a cosine squared. So let's take a look at the formulas, our double angle formulas. And if you remember, there's actually 3 formulas for that. So for cosine 2 theta, you can either have cosine squared theta minus sine squared theta. It doesn't look like that one's going to work because I want to make it into a cosine. There's another one that has 1 minus 2 sine squared theta. That also is not going to work because I want this one to, we don't want to have 2 different trig functions. So it looks like our other alternative will be 2 cosine squared theta minus 1. This one seems a little bit feasible because it has a cosine. So I'm going to replace this, so I have the 9, the cosine 2 theta, I'm going to replace it with that identity. So 2 cosine squared theta minus 1 equals 9 cosine squared theta minus 4. So this will give me 18 cosine squared theta minus 9 is equal to 9 cosine squared theta minus 4. So let's go ahead and move the 9 cosine squared theta. Okay, so I get 9 cosine squared theta minus 9 is equal to negative 4. So let me add the 9 over. So I get 9 cosine squared theta. So I'm going to take that 9 and I'm going to subtract 4. I'm going to get 5. And what you're going to get is going to be cosine squared theta equals 5 over 9. I'm going to take the square root to both sides, plus or minus. So cosine theta equals plus or minus square root of 5 over 9. Alright, so clearly this is not quite going to give me the answers that I want. This is not in the actual unit circle. Okay, so we're going to have to improvise. Remember, take cosine inverse. So I'm going to take the cosine inverse of 2 equations of the positive square root of 5 over 9. Oh, there should be a 3. And I'm also going to take, so that's going to be my theta 1. Theta 2 is going to be also cosine inverse of the negative square root of 5 over 3. Okay, so let's see what that gives me. So if I go into my calculator, cosine inverse of square root of 5 over 3, that's going to give me about 0.73 radians, okay, which is basically in quadrant 1. So this is one solution. My other one is going to be the negative square root of 5 over 3. That's going to give me 2.41, which is basically over here. And the reason why I know that is because remember, cosine inverse has a restriction from 0 to pi. So we know that it can only be between those two values, between these two guys. All right. So these are two solutions. Now we got to find the rest of them because it's between 0 to 2 pi. So here's pi, this is 0.73. So there's another solution down here. So all we got to do is just add pi to that. So theta 3 would be 0.73 plus pi. And then theta 4 is going to be, well, I know this solution is in quadrant 2. My other one is going to be out here. So I'm going to add pi to that too. So 2.41 plus pi. So you're going to get 0.73 plus pi. That gives me 3.87. And my other one's going to be 2.41 plus pi. It's going to give me 5.55. So these are all 4 solutions that I got. Okay. Now again, if I wanted all solutions, I probably would have stopped here at the 0.73 and 2.41. And I would have just added plus pi k to both of these guys. And then be just done with it. Okay, so that's some trig equations. There's a lot more to them, but that's basically the gist of it. So you have most of the tools to be able to solve a lot of them now.